Hello everyone, good morning, good afternoon, and good evening to all of you, distinguished delegates, presenters, and participants from SARC member states and other regions around the globe. I am thankful to all of you for joining us in this SARC webinar on energy simulation of building. My name is Tularam Paudel and I am working as Research Fellow Energy Trade at SARC Energy Center, Islamabad. I shall be moderating today's webinar. Ladies and gentlemen, SAG Energy Center is carrying out lots of research and start to find out energy saving opportunities in various sectors of energy usage in South Asian region. In this time, we are focusing in building and we have organized this webinar. The energy consumption of a building is a complex function of vast number of interrelated processes such as local weather, occupancy, type of load, operation schedule, expected level of comfort, material used in building envelope, geometry and facing of building and other various schedule and random variables. For the design and operational decision of an energy efficient building, correct estimate of this variable and process are needed. For that reason, energy behavior and performance of variable of building are modeled and computer simulation is carried out. Based on the result of simulation, refinement in the process and variable are determined to have an energy efficient design of building. Such simulations are increasingly used as tool for designing, operating and retrofitting of the building to meet the energy and environmental requirement. In this webinar, we'll try to cover the topics introduction to energy simulation as fundamental ideas. Expert will be discussing the range of simulation tools, model of buildings, their application. We'll be enjoying with the building energy simulation is being practiced in Australia and China and South Asian region. The participants of today's webinar are from relevant government department, research organization, academia, energy professional around the world. Now it's my pleasure to inform that Mr. Muhammad Naeem Malik sir, Director, and Dr. Shoaib Ahmad, Deputy Director of SAG Energy Center, have also joined us in this webinar. We are very thankful to you, sir. I am also extremely grateful to our panel of presenters, Mr. P.C. Thomas from Team Catalyst Proprietary Limited, Australia, Mengling Wang, Beijing Glory, PKPM China, and Mr. Asad Mehmood, National Energy Efficiency and Conservation Authority, Pakistan. I thank all of you for accepting our invitation to participate in our webinar. I shall introduce them in detail before the start of the relevant session. Our first expert is Mr. P.C. Thomas. He is a founding director of Team Catalyst Proprietary Limited with the motto driving sustainability through teamwork. Thomas is also adjunct associate professor at the University of Sydney. He has a master's degree in mechanical engineering and 30 years of consulting, research and teaching experience in sustainable building, building energy simulation, energy auditing, energy efficiency in building and solar energy. Mr. P.C. Thomas specialized in integrated building design using simulation tools to assist in the design and delivery of sustainable building, in particular in predicting the performance of mechanical services. He understands the philosophy of all green buildings rating scheme in Australia that relate to non-residential building, namely the National Australian Building Environment Rating Scheme, NABERS, the Mandatory Commercial Building Disclosure Scheme, CBD, Green Star equivalent to lead, and Section J of Building Code of Australia. He is involved at some level with teaching, developing, or reviewing each of them. Thomas enjoys working in a team environment to help design and retrofit building to deliver sustainable, high performance buildings. Dear participant, before I hand over the control to Mr. Thomas, I would like to inform that you will have the opportunity to ask questions to presenters by typing your question or clicking to the raise hand option into the attendee panel of the main window of GoToWebinar software. You may send us your question at any time during the presentation. We will collect and address them during the question and answer session at the end of his presentation. Over to you, Mr. Thomas.
Thank you, Mr. Tularam, how are you?
Yeah,
I
fine,
just
sir.
want to, yeah, I just want to check, can you see my screen now?
Yes, yes, yes. It's visible.
Okay,
Yeah, you can
all
go.
right. Thank you very much. So, well, thank you for the kind introduction and thank you for this opportunity to present to members of SARC. It's a very great honor for me to do so. So today I will talk about an introduction to what building energy simulation is. I've been teaching at the University of Sydney for the best part of 15 years, and I usually start the courses on energy simulation with a lecture something like this. And that is really because many people have different ideas about what is energy simulation or what is building performance analysis or things like that. Everyone has a slightly different understanding, but once I think it's always useful for us to get together to understand what simulation is about and how do we go from there. So without further ado, let us get into the presentation. Now, one has to ask, why should we do energy simulation? Why should we predict the performance of a building? So there are two main reasons. If you are looking at an air-conditioned building, then because we have a requirement for reducing greenhouse gas emissions, because our planet is warming, we are trying to find what is the least amount of energy that is needed to maintain comfort. And everyone has a slight definition of comfort. We'll talk about that in a second. However, if you are looking at a non-air conditioned building, one that is naturally conditioned, then energy really has no meaning. You are then interested in looking at how many hours can you keep a nominated space comfortable. These are in my view, these are the two major reasons for why you do energy simulation. Now, I spoke about comfort. About 10 years ago or 15 years ago, when air conditioning engineers talked about comfort, they only talked about temperature and humidity and some air movement in the space. The air conditioning system would provide some fresh air. It would do some filtration to clean the air. But that was the range of what we looked at when people spoke about comfort in buildings. Of course, since that time, that definition of comfort has been broadened, and you can see the other points on the screen: noise levels, lighting, glare and contrast, furniture. All of these things then start to become part of comfort. In modern buildings and modern analysis, we talk about using a comfort metric. And one of the metrics that we use quite often is this one. It's called a PMV, or a predicted mean vote. And you can see on the right-hand side of the screen, there are 6 variables: air temperature, radiant temperature, humidity, metabolic rate or activity rate, how much clothes are you wearing, and what is the air velocity in the space. All of these are combined to predict a vote about how many people are dissatisfied. Now, the interesting thing to kind of note on this chart is that when the predicted mean vote is close to 0, it is called thermally neutral. But even at thermally neutral, 5% of people are not satisfied with the comfort in their space. And that's because human beings, each one is different. I prefer a slightly warmer space. I have colleagues who are from New Zealand, where it's much colder. They prefer a much cooler space. So we can never really agree on what is exactly comfortable. We both have slightly different ideas about comfort. But in many cases, if you can keep the predicted mean vote somewhere between plus and -1, it is considered to be in a range that is acceptable in an air-conditioned space. A PMV has no meaning when you're talking about unconditioned or naturally conditioned spaces. So how do we do this? Well, we are doing this performance prediction by developing an energy simulation model of a building. And on this slide, I have got all the components of the energy simulation model typically. And we're going to walk through this slide from the bottom of building geometry and materials and go all the way around. So I might come back a couple of times to this slide to as I'm talking about it. So the first part is you have to represent the building geometry correctly. So for example, here is a building that we worked on almost, I think now 10 years ago. It was built 25 years before that. So we were doing some refurbishment on the mechanical systems. But if you look at these pictures, the top left-hand corner has got a picture which shows overhangs in front of the windows. And Australia is in the southern hemisphere. So for us, the sun always comes in from the north. Now this is completely reversed compared to the southern hemisphere where, the northern hemisphere where all countries of India and the SARC countries are located, Pakistan, Bhutan, Nepal, they're all, for you guys, the sun is always coming from the southern part of the sky. So I'll ask you to please excuse me when I talk about directions. They are opposite to what you are normally used to. But anyway, if we call this the sun side of the building, you can see here that the sun is hitting the wall, but the overhang is shading the glass. And that's what it was designed to do in summer. If you look a little bit around the edge of the building, you can see there is a screen here, which is designed to stop the western sun hitting the windows directly. And you need to be able to represent all of these things in your model. On the lower part, on the left-hand bottom corner of the screen, there is a little outline drawing that I have made, which has got the words or the letters A, B, and C. Now, this is a division of the building, which is not made by the architect, but it is a division of the building made by the mechanical engineer, the air conditioning engineer. He has divided the building into 3 parts. Each part is served by one system, and I'll show you that as we go along. On the top right-hand corner, you can see another view of this building, and now that is the eastern facade that you can see here. On the bottom, you can see the south-facing facade, and you can see clearly there is no sunshine on this facade. This is equivalent to a north-facing facade in the SAARC countries. So it's the non-sun side of the building. Now here, that's the real building. And on the left-hand side here is our simulation model. you can see that it has got faithfully represents the geometry. The geometry has been developed in a software called Design Builder. You can see that. On the models on the left, the dark gray parts are the opaque parts. The light gray parts are the transparent parts, and that's where solar radiation can interact with the building spaces. And the purple parts are really just shading devices. So there, the role of the purple parts is to stop the sun from hitting below that. So if you look at the bottom figure, then on the right hand side, you can see some vertical screens that are shading the windows. And those shading screens have got some transmittance data, so they will be stopping 30% or 50% of the sun's energy coming through into the windows. On the right hand side, there is a model of a house. Now that is quite different from a model for a commercial building, because generally we might be looking at performance prediction of comfort without using heating and cooling systems. And I've got this in a visualization mode where you can look at how the sun is approaching the building, and you can see at a particular time of the year how the sun is penetrating through the windows onto the floor plate. Anyway, so that's the first part. You've got to represent the geometry correctly. And then you've got the most important next part is windows, because windows are the next weak link in energy coming through the building. So I have a picture on the screen now where you can see two window pieces. The window piece on the left is a little bit darker. The window piece on the right is a bit brighter. There are three performance parameters that we typically talk about when we talk about windows. And you can see here that one is solar energy, so solar heat gain coefficient. There is daylight, so sometimes we call that visible transmission or daylight. There is a U value, and we'll talk about that in a second. So the solar heat gain coefficient determines how much of the solar energy, the short wave energy from the sun, enters the building. So if you look at the picture, you can see the numbers are written below that. And you can see that the solar heat gain coefficient is approximately the same for both pieces of glass. The one on the left allows 54% of the solar energy to come in. The one on the right allows 55% of the solar energy to come in. They both are exactly the same. But the light transmission is very different. The one on the left only allows 14% of daylight to come through. The one on the right allows 63%. So you can see that it would be much more pleasant to sit in a room where you have more daylight. Of course, if it's a really bright country, it's very hot, that might not be what you want. So depending on your situation, you would be picking the right sort of glass. Now, glass has got some very interesting problems. You get the properties at the center of the glass, but then the glass is put inside a frame. The frame has got its own properties, and the combination of them we usually use for doing modeling. So we call that the whole window system properties. And that itself is quite a complex problem. And there are specialized softwares which we can use to compute the full window performance. If you're using a metal frame, then that might actually bring down the performance of a high quality glass system if the frame is not thermally broken, as we call it. And these kind of details need to be included in the model to make sure that you're getting the right sort of outcome. So in addition to providing glass properties, you also need to provide construction properties. So, when you have a wall, you have more than one layer. You might have a brick layer, you may have an air gap, you might have some insulation, you may have some plasterboard. So these layers need to be provided to the model in the order that they are constructed. And that is really about the model being able to compute how much energy is being stored in the structure and released at a later time. Okay, so though I have not got a slide on that, but that's another one that you need to think about. Then you need to think about how do you divide the building into a series of zones. And we talk about thermal zones. And the idea is that a thermal zone works in a similar way when you talk about heating and cooling requirements or thermal comfort conditions for the occupants. Now I've given you the same building and I've given you a screen which shows how we've divided that building up. If you remember the A, B, and C that the mechanical engineer had, you can see the representation of that A, B, and C. You can see where the three systems are. On the left-hand corner, the right-hand corner, and the bottom corner, there are three systems. And there are certain air handling units which are doing zones, some zones. So if you look at the bottom three, there is an orange zone on the east side of the building, another orange zone on the west side of the building. Each of those has got its own air handler. And then the blue part is an internal zone. So the difference between these perimeter zones, or the zones that are near the edge, and the center is that the zones on the edge will interact with climate. The sun will fall on the external wall and window. Temperatures, wind speed, rainfall, all of these will affect the external walls. But the inside zone, the internal zone, doesn't really have any of those interactions. If the air conditioning engineer chooses to put fresh air in, then that is the only interaction that that internal zone has to the outside. And therefore, there's a separate air handler which is conditioning that internal zone. So if you think about it, in the morning, the east zone will need more cooling because that's where the sun will be hitting the wall. In the afternoon, the west zone will need more cooling. That's when the sun will hit on that. And the internal zone may not have too much of a change if it's an office type building. So this zoning is quite important, and it's a kind of dance between the architect and the mechanical engineer to decide how the building is working. In this case, it's an open plan office, so some of this zoning is virtual. There's no real wall there, but there is a heat transfer boundary to allow the simulation software to do its calculations. Now, zoning a commercial building is very different from zoning a residential house. In a residential house, as you can see here, I've broken it up into a living zone, a kitchen zone, a corridor zone, bedroom zones, toilet zones. There's a garage here. So there it's more by use. So that's the way zoning is. But in both cases, you need to provide zoning for the model to work. And then in each zone, you need to describe certain properties that the model will use. So if we go back to my slide, we've just finished building geometry and materials. We've talked about windows and frames. And now we're going on to building loads. So the question is, why does a space become uncomfortable? Why do we need air conditioning at all? And this slide explains the basic 4 building heat loads that an air conditioning engineer has to consider, and which the model also has to consider. So solar radiation, shortwave radiation, comes through the transparent part of the building envelope, so through the glass. And then the shortwave radiation hits something. Could be the floor, could be a wall, could be furniture, could be a person. Once it hits something, it converts to long wave radiation. And long wave radiation is opaque to glass. So the long wave radiation goes out of the building much more slowly than the solar radiation comes into the building, which is why we have parts of the building become really warm, which is also the reason why we have the greenhouse effect in the earth. Our CO2 layer in the atmosphere acts like the glass. It allows the shortwave radiation to come in, but it doesn't allow the long wave radiation to leave the Earth's atmosphere very easily. That's one. The second number of load is internal heat generation. So anything that is creating heat inside the building. For example, lights will release heat, computers, fax machines, printers, all of those things will release heat. People will release heat. Um, Those are all heat sources within the building, again, which might require the room to be cooled to maintain a particular comfort level. The third one is temperature difference. So, there is a temperature difference outside, and you want to maintain a temperature inside, or a temperature range on the inside. Suppose it's a warm country, which most of the SARC countries are. And then the outside temperature is 35, 36, 38. The inside, you want to keep it somewhere around 24, 25, 26, whatever temperature you choose. The heat is going to try and come in. That temperature differential is going to drive the heat coming in. And the material property, usually we either call it a U value or an R value, that'll determine how fast the heat is coming in. And the model needs to know that. Okay, that's number 3. Number 4 is air exchange. Okay, and there are 2 kinds of air exchange. So we'll talk about the 2 of them. One is ventilation. Ventilation is what you want to give. So, you have a fan, you know how much air you're putting into the space. That's ventilation. The other is infiltration. Infiltration is ventilation that we don't want. It depends on the quality of building. It is the leakage of outside air coming in or inside air going out. So air coming in may be warm, air that is in the room may have been cooled. If that leaks out, then you're throwing energy away. So that needs to be considered. So these are your 4 main components, and the models need to be told about these things. So let's have a look at these internal heat generating components. Let's talk a little bit about that. Okay. So in Australia, for example, in our National Construction Code, the lighting component of energy cannot be more than 4.5 watts a meter squared for an office building. Now that's quite an efficient lighting system. And so there's very little heat being provided by that system, but it is still there. It needs to be counted in the model. Typically, when you are talking about lighting systems, you're interested in what are the lighting sources that you're using. You want to purchase the most efficient components. You want to combine them all into a system. And you want to switch off the lights when you don't need it. So you need a control system that looks at doing this switching. Now, in addition to providing this, you want to tell the program, how does this lighting system work? When does it come on? When does it switch off? How much is it on? Okay. So we have to develop what's called a schedule or a profile of how these systems work. And I'm showing you a profile that we developed when we were modeling a library building in Australia, a university library building. So we didn't know how libraries worked at that time. So we went and talked to the librarian, and the librarian told us, you know, these postgraduate students, these doctor students and master students, they don't know about holidays. You know, it doesn't matter whether there's a religious holiday or a public holiday, they are in there every day of the week. So 25% of my rooms have to be lit all day, all through the year. So you can see my minimum here is 25%. Then most universities in Australia used to run 2 semesters. So, you know, we would have holidays in January and a part of February. Then people would come to the university. They would have a few weeks of teaching. They would have 2 weeks of break, then another few more weeks of teaching, and then they would have exam weeks. And of course, at exam week, every single room, every single space in the library is full. So 100% of the lighting system is running during those exam weeks. So that's how we built a profile, and that's what we fed into the model. You know, and this needs to be done when you're doing energy simulation. Now, how can you save energy if you are trying to consider daylight? Well, that starts to get a little bit complicated. Here is a prediction of daylight inside a room when there is an overcast kind of sky, okay? And you can see here the daylight near the edges where there are windows is very high. And as you go into the middle of the room, the daylighting drops off. And by the end, inside the room, there's no daylight that is useful. Now, if you want your model to consider the energy saving that is possible through the daylight, you need 2 things. You need, one, a model to predict how much daylight is there every hour on your working plane, on your working surface. And 2, you then need to have some linkage between your electric lighting system and the daylight levels on your working surface. And you need a control strategy which tells the lighting system there's enough daylight now, and you can turn down the lights or you can switch off the lights at this point. Okay, unless you have that, there isn't much point in trying to model daylighting in your system, and most models can't do that very well. You need specialized models that will allow you to do that. So here's a daylight analysis of that house model that I showed you, and you can see how they work. Okay, so you can see which pits have got more daylight, which pits don't have much daylight. Okay, that's lighting. The second one we need to tell the model about is equipment. You know, equipment produces heat. You're inside an office, you're using computers, screens, laptops, fax machines, printing machines. You might have a small kitchenette where you've got some coffee and tea kettles going. All of those things use energy. All of that energy becomes heat and comes into the spaces. You need to tell the model about that. Okay, I won't go any more into that. That's sufficient for now. The third thing here is about people. Okay, now when you design an office building or you design any other kind of building, you have some criteria. So in Australia, when you design an office building, you're supposed to provide 10 square meters per person. Now, I believe it's a little bit lower in the SAARC countries. It might be 8 meters squared per person or 5 meters squared per person. That's fine. Okay. You need to tell the model what it is that you're designing for. This is your maximum design occupancy load. Then you need to make some assumption about how much heat does each person generate. So we talk about heat being either sensible, which you can feel, or moisture, latent energy that a person puts out. So you have to account for it. Your model has to account for it. Okay. Then because there are people, you need to provide outside air, fresh air, air where when the oxygen is not depleted. If you don't provide fresh air, after a while people will start to yawn and feel very sleepy, and it might get worse. But you need to provide fresh air. It's mandatory in most countries with air conditioning to provide outside air. Now the other thing is, you don't always have 10, one person every 10 square meters. That is your design peak load. But you need to make some assumption about how this occupancy load varies over time. So again, you have some sort of a schedule. I've shown you the schedule that we use in Australia for our national construction code when we are doing energy simulation. We have a different schedule from Monday to Friday, and then a different schedule on Saturdays and Sundays. And you can see here, I have sort of highlighted a region. So from about 10 o'clock in the morning to about 6 o'clock in the afternoon, we have more than 20%. And that's the time when we are interested to ensure that we are maintaining the best possible comfort within each space. On the right-hand side, I've showed you how that shows in a graph. Okay, so you need to have a schedule for people, for how lights work, for how you use your equipment, when your air conditioning systems come on and come off. All of those things need to be provided to the model. Okay, so if you go back to our chart, you can see that I have covered building geometry, I've covered usage schedules, internal loads. I've covered lighting systems. So the only system that we now need to look at, or one of the only systems that we only need to look at now, is air conditioning. Okay, so let's talk a little bit about air conditioning. So the basic philosophy of air conditioning is like this. And typically in the SAARC countries, you're doing cooling, you're not really doing much of heating. So this is an appropriate slide. In air type systems, we are providing cool air into a zone. This cool air is picking up sensible heat and latent heat, moisture, and then you are then extracting that air out. We call that return air in air conditioning terminology. That return air is sent to an air handling unit. It is cleaned, it is filtered. Some part of it is thrown out. Some part is replaced with outside air. Then you send it to get cooled, and then it comes back as supply air. So the mechanism to do this cooling is represented in this slide. Your zone is on the left-hand side bottom corner here. And you can see there's a number of pieces of equipment that are required to do this cooling of the air. So there is a air loop, there's a fan which blows air into the zone. There is a cooling coil, that's the bit that provides, which makes the air cold or cool. There's a filter which traps the biggest particles that there are, so you get clean air coming in. You exhaust some of the air that's coming back from the room, and that's this EA over here. And whatever you exhaust, you bring in as outside air. That's usually the warmest air that's coming in, and then you mix it with the return air, and then you filter it, you cool it, and you blow it into the room. Then you might have a chiller, and the chiller will circulate chilled water through the cooling coil, and therefore it'll need a pump. So the pump will push through the evaporator side of the cooling of the chiller. There is a compressor that will there's a pump, and there is a monitoring device there which decides what is the temperature that's going on. There's another part to the chiller which is actually the refrigerant loop. That is the loop that makes this chilled water, and that happens inside a loop where there's an expansion valve, there is a compressor, and then between there are two vessels, an evaporator vessel and a condenser vessel. So by making, if you want to think about it as an example, you can think of the fridge in your house. You open the door of the fridge, you put your food into the evaporator, which is the cold part. If you reach around and touch the back of the fridge, you might find that the fridge is quite warm. That is the condenser part of the fridge. That's where, to make this part cool, it's extracting heat, so it becomes hot. Okay. How do you get rid of the heat? In this case, you have a cooling tower. The cooling tower essentially is a spray of water which evaporates and cools the water. So essentially, this whole thing, the system is basically removing cold from this conditioned space, taking it through all these loops and chucking it into the atmosphere. That's the role of an air conditioning system. Now, if you have a split system in your house, you don't have these two water loops. You don't have a chilled water loop. You don't have a condenser water loop. Instead, you have this refrigerant loop that directly cools the cooling coil. And you have a fan which blows air across the condenser, which sits on the outside. And that's what's trying to cool the condenser. So it's the same thing, but with less number of parts. Okay. So that's not all. You have one more loop in the air conditioning system, and that's a control loop. Now, why do you need a control loop? Well, as an air conditioning engineer, I'm designing a system for some particular design day, and that design day is a weather condition. And my role is to say that as long as the weather doesn't get beyond that design day condition, I can keep the spaces cool with the size of the air conditioner that I'm using. Now, the definition of that design day is actually based on a confidence level. We can talk about it as being a 1% design day or a 2% design day. And the idea behind that is that this weather condition is not exceeded by either 1% or 2% in the year. Of course, what does that mean? I'm sizing for this air conditioning system for 1% of the year. So for 99% of the year, my air conditioning system is too big. So what is an energy efficient air conditioning system? Well, an energy efficient air conditioning system is simply one that in the 99% of the year, when you don't need that full capacity, it is able to ramp the capacity back in an efficient manner. If you can do that, then you're done. And that's what the energy simulation is trying to do. It's trying to replicate a control strategy that you've thought about. What's a control strategy? Well, when you don't need the full capacity, you may be able to slow down the fan. You may be able to have not so cold supply air. You may be able to slow down the amount of chilled water you're pumping. You may be able to slow the compressor for the chiller. You might be able to slow down the cooling tower fan, or you might be able to slow down the amount of the condenser water. There's many options possible. That's what the problem is. unless you have a view of the air conditioning system and which strategies work, which strategies don't work for that particular configuration of air conditioning systems, you really can't do a good energy simulation. This is the one part in our industry where there's a big lack of knowledge, and that's the part I like to teach about. Everyone knows, well, not everyone, but a lot of people know how to make the building envelope efficient, but they don't know which kind of air conditioning system to choose, which control strategy to use, how to size it. That is the part that we really need to understand well. So here's my representation of exactly what I just showed you inside this energy simulation program. Here is a zone where I am going to be providing comfort. That comfort is going to be provided by this air handling unit, which has got a fan to supply the air in and another fan that pulls the return air back. There's a cooling coil there that makes this fan cold. There's a controller that decides the control strategy for this loop. This cooling coil will be having chilled water pumped through a chiller. The chiller will have a pump. It will have a controller which decides how it's going to chill the water or how the chiller is going to operate to chill the water. Because it's a water-cooled chiller, the chiller gets hot and the chiller needs to reject its heat. It does that in a cooling tower. The cooling tower has got its own pump and controller. So you can see it's quite a big, complicated system. Now, in Australia, we do need heating and cooling. So we have a boiler. The boiler provides heating to a heating coil. There's a pump and a controller. I doubt you will be needing much heating in the SAARC countries. So, you don't need to worry about that part of the system so much. Okay, there's our simulation model. So what happens now? Well, you have your model on the left-hand side of the screen. You need a weather file because you need to tell the model how does the weather vary every hour in the location that you're interested in. Then you need a simulation engine with all the equations of heat transfer, mass transfer, all of those, and about how chillers work, how fans work, how thermal mass stores energy, how thermal mass releases energy, how does the sun impacting the window at a particular angle, how much of the energy comes in, how much stays out, how much is reflected out, how much is absorbed in the glass. All of that stuff is part of your simulation engine, and we use Energy Plus a lot because that is developed by the US Department of Energy. That's a very robust engine that we use. Okay, so we've run our energy simulation model. What are we looking for? Well, at the end of the day, we want to say something about, how much energy do the lights use, the equipment use, and then all these little bits, pumps, fans, chiller, boiler, all of that that we need. Now, this is for Australia. Our winter is now, June, July, August is winter, so you can see there's a lot of heating going on. Our summer is in January, February, and December, and summers in Sydney and Melbourne still have a few cold days, so we do use some heating. We may use some heating, particularly in Melbourne, on what is our summer as well. What else can we learn? Well, if you looked at particular days and particular zones, you can start to map things about what's going on inside the building. So here is a zone, and the red line is the temperature outside on the bottom graph. Okay, and inside the zone, my air conditioning system comes on at somewhere around 6:30. And it keeps a mean air temperature within the zone. I think I've set this thermostat at 23.5, and that's what it's doing. Okay. But what the person in the zone perceives is not the air temperature. The person in the room perceives a mean radiant temperature. Sometimes we call it globe temperature. And you can see here, it's fine for quite a long time, but suddenly it goes up. Why does it go up? Well, this is a west-facing zone, and the sun starts to fall on the glass around just after noon. And you can see this yellow line on the top graph, it increases, and that's when the radiant temperature also goes up. And that's when the level of comfort starts to exceed what you would like. It exceeds 1. So you're saying that this time is getting uncomfortable in the space. Now you can change your building envelope to adjust this. You can adjust the air conditioning system to give you more cooling when you need it at that time. All of those things are possible. So then the thing becomes that you spent the time and money to build the first model. You should be doing a series of options to get to where you want to be. So I think at this point, I'd like to leave it because I think we've exceeded our 40, 50 minutes. I was going to also touch a little bit about how to do simulation of unconditioned buildings, but I think we can leave that for another time. It's probably a good time for us to do some question and answers. So if you have questions, maybe either the moderator can take over and ask participants to ask the questions, or you can provide the questions in the chat box and I can respond to that. Thank you.
Hello. Oh,
Yes.
thank you very much, Thomas sir, for your very clear, informative, and meaningful presentation. Because every energy aspirant of the building simulation should understand and go through the concept as you presented. Of course, we have some questions, sir. I want to request you to stay over there.
I will. Thank you.
Okay, sir. One question from our participant is he's asking that did the day lighting aspect is considered in the simulation?
You can. It depends on the program you're using and the skill of the modeler, but you can link a electric lighting systems control to the prediction of daylight every hour, and therefore you can then work out what is the saving in electric energy use for the lighting system. Now it depends on what you are trying to achieve with the energy simulation program. In India, you have got the Energy Conservation Building Code, ECBC it's called. And in that, they do require a daylighting analysis. So that becomes part of the simulation program. In Australia, for compliance with the National Construction Code, at this point, we don't consider the improvement in lighting energy by daylighting. And one of the reasons we don't do that is our lighting systems are so efficient now that there's very little saving that we make from daylighting. However, having said that, there is a separate analysis required, which requires the user to show that his design has got a minimum level of daylighting in a particular percentage of the floor area for a particular amount of time. I think there are 3 or 4 simulations of that type available. There is one called the UDI, I think it's some utilizable daylight index. There is something called an SDA, and there's one more, I forget at this point. But these are being used around the world to show the impact of daylight. Daylight has got a health benefit, obviously, as you know.
Thank you, sir. We have another question, and our participant Muhammad Ajad from Pakistan is asking, is the use of renewable energy aspect as for the building location is considered in the simulation?
Again, it depends on the model. The models we use allow you to place either a solar PV electric system and generate electricity and offset that against the consumption of the building. You can do that. You can also model solar hot water systems. And if you have a hot water demand, then you can offset the hot water demand by modeling those systems. The yeah, I mean, you have got a number of module characteristics. You have some maybe less sophisticated inverter battery models, but they are available within these systems. Yeah.
Okay, perfect, sir. Sir, you talk, in your presentation, you talk about the lighting load inside the building, mainly considering the window and its material. So, in some country like Thailand, I have visited the building where the daylight is used by through the pipe, or it is collected at receiver and carried inside the room through the piping, special type of piping design, and the intensity of lighting is adjusted at the receiver side. So how have you practiced in Australia, and what is your experience on that?
Okay. Um, I think we are probably not as sophisticated as some of the SAARC countries in terms of daylighting. We have some very good products for the residential and small commercial scale. Let me show you, let me see if I can just show you another slide where I can talk about that. So for example, let me show you this screen. So this is a daylight model we had done for a residential building. There is a renovation going on this part. So this is the new part. This is the old part. So you can see the old part is much more dark. And if you look here, this part where left-hand middle of the slide, it says you can make out the word kitchen. And you can see that, you know, the right-hand side of the kitchen has got some light. The left-hand side of the kitchen is very dark. So if you get an analysis like that, you can use it as a design device, because what was done was that because the architect and the occupant realized that this part is going to be dark in the kitchen, they put in a product something like what you have said. So, you know, if you see on the right hand picture on the top there, this is post construction. That is not an electric light, that is a solar tube light. And there is a very highly reflective tube behind this light that goes to the outside of the roof, and there is a dome on the top which collects daylight and transfers it into the building. So, you know, you can use these kind of models to allow you to make decisions on design, which is quite useful. So it's not always about predicting a performance, but you may use it as a design tool. And then it's quite easy to do things like that. Any other questions?
Okay, thank you, sir. We have some question, more question. One participant, Sankara Naran, Maharashtra, maybe from India, is asking, what is the gap between actual building energy performance compared to simulation energy assessed?
That's a very good question, and thank you very much for that. That is very dependent on you know, how you use the simulation tool. Okay. Typically, when you use it for national construction code compliance, you model a reference building and then you model your proposed design and you show that your proposed design is better than your reference model. But those kinds of models generally have no relationship with um, the the actual energy use. Now, the only way you can do that is when you have a rating system which actually allows you, or which makes you compare the, or gives you a rating based on uh, the the electricity bills. Now, you don't actually see that very often in the world, but in Australia, we have this system called Neighbours, and you may want to go and look at that. And in Neighbours, what happens is that the rating is provided based on 12 months, 12 previous months of electricity and gas bills and the area of your building. So the rating doesn't care about the simulation. It doesn't ask any questions about the simulation. It just says, okay, give me 12 bills and give me your conditioned area and a couple of other things. You can actually go to the Neighbours website. I've given you the link here, neighbours.gov.au. And there is an online rating system. It's a very simple rating system. There are only 5 inputs, but there's a very rule book on how to get those 5 variables, because as soon as you put a rating system out, everybody wants to cheat to get a better star rating. But you see, what happened is that in our industry, the developers who are making new buildings then came and said, how can we make a commitment to say that we are going to deliver a building which will perform to a 5-star rating? How can we do that? And the government said, okay, you sign a legal commitment with us.
Okay.
That will
Okay,
allow
thank you.
you
Perfect.
to, yeah, that'll be.
So another question from Tibin the Powder is asking about the unconditioned room space. How to go about the simulation for naturally vented building?
Yeah, you can do that too. The same sort of models will allow you to do naturally ventilated buildings. Now, this is a example of a house that we modeled where we were looking at, okay, let me show you a summer chart because that will be quite interesting for you. So here's the house with west-facing windows, and in summer, the sun is high in the sky and a lot of energy is coming through the west-facing windows. So what we have done is, if you look at a visualization of that, so at 3 o'clock in the afternoon in summer for us, you can see that there's a lot of solar energy coming in. So I'll show you this graph, which is actually comparing 2 energy simulations, both using natural ventilation. So there is no air conditioning playing up. The bottom graph is temperature, and the green line is the outside temperature. The red line is the mean radiant temperature that the person feels inside the space. Okay, and you can see here there are 7 days, 1, 2, 3, 4, 5, 6, 7. And in the afternoon, because it's a west-facing window, you get a lot of solar energy coming in. And because you get so much solar energy coming in, the room is very uncomfortable. It's 40 degrees centigrade in terms of mean radiant temperature. So what should my design approach should be? So I'm going to put an external blind on the outside of the window That's this blue line on the top, which is going to cut all the solar radiation from coming into the space. And the minute I do that in the second simulation run, I can see that the 40 degrees has become 32 degrees. So the simulation is predicting what is the impact of having a blind that you can schedule. So that's the blind on the outside, and that was the simulation that showed you what's going on. In addition, you can predict how the airflow varies every hour because of the simulation. So the blue arrows tell you how the air is going in through certain open windows, and the red arrows tell you how the air is going out through certain windows. So this building has got no air conditioning, but we are using the simulation to try and predict comfort. I hope that answers the question.
Okay, that's perfect. Actually, I think you nailed question. So we have another question from Milad says to Nepal, and he's saying, can you in shortly tell us what would be the comfort for on air conditioned space?
Oh, yes, I can do that. Now in Nepal, I know that it is cold, so let me talk about cold. Okay, the same model we looked at summer and we looked at winter. So let me show you the winter an analysis, right? So in winter, the sun is low in the sky, and you can see here that it is hitting the east wall, and I'm getting a sun patch inside the house. But when we looked at it carefully, you know, the sun is only there for 1 or 2 hours, and then this ridge comes in the way. Okay, so this is in the morning. Okay, now look at this picture of the sun coming through into the building. We took a picture of it post construction, and you can see the prediction was very accurate. You know, the same kind of thing is coming through. In the afternoon, the sun comes through, but again, it is blocked by this ridge after a couple of hours. So, you know, we were able to show that post construction. Again, you can see what's going on. So what should be my design response? I should have insulation underneath the floor, insulation in the roof, insulation in the walls, double glazing in the windows, and then we are able to do a simulation where we are doing what you call a free floating analysis. So no air conditioning, and you can see this is the month, is a winter month for us. The green temperatures show you what is the outside temperature, and the red and blue lines show you what is happening inside the room. And in what I can say is that when the temperature is 2 degrees outside, without any heating or cooling, the lowest that my room is getting to is about 12 degrees centigrade. So that kind of prediction you can do. Then you can take these hours and put it into a spreadsheet file, and you can say how many hours will be comfortable. And this is a living room, so I'm looking at 8 a.m. to 10 p.m. and I'm saying that about half the time my room can be shown to be comfortable by doing this sort of simulation.
Okay, that's perfect. Thank you, sir. Sir, I have one question, but it is a bit deviated from what you shared with us. So, one question is, what major type of sensor are used in building to keep them comfortable for the users? Sir, you have any idea on this?
What major type of sensors?
Sensor, yeah.
Yeah, I mean, look, in most houses, the only sensor is the thermostat that is on a wall somewhere. You know, but and usually in most houses, the only sensor you're using is well, the only control you have is the remote control for your reverse cycle air conditioning system most of the time. Of course, there are many other sensors available. I believe you know Dr. Rajan Rawal at CEPT. He is developing I think like a radiant temperature sensor or an operative temperature sensor, which can be used to control air conditioning systems. That's quite an innovative sensor, and there are now many digital types of controls available as well. We can talk offline if you want. That's a different topic.
Okay, thank you, sir. Of course, we have some more questions, but due to time constraint, we have to cut off the session here. Thank you, sir, very much for sharing your ideas and opinion with us. Of course, we will be talking to you in offline and in coming time with our queries. Thank you very much.
Thank you. I will change presenter so you can take over. Okay.
Thank you.
Shall I give it to Miss Wang, or will you do that?
No, we'll give, sir. Thank you.
You'll give it. All right. Thank you very much. Thank you, everybody.
Okay, thank you. Then, okay. Our second part speaker, Miss Meng Wang, and she's from China. She has been working as a software product manager for over 7 years in Beijing Glory PKPM, which is one of the biggest building design software development company in China. Our major work and research scope are the design and development of building energy saving simulation software and green building simulation software, and she has participated in the preparation of several relevant Chinese standards. Over the past few years, she has accumulated a lot of practical experience of software application in engineering practice. The PKPM software developed by her team now is the most widely used building simulation analysis software in China. Her team and their products have helped many architects and project owners solve problems like building energy efficiency, environmental comfort, air quality. Okay, I want to invite to maybe one, please, over to you. Yeah, maybe one. Are you there?
Yeah, hello.
Okay, hi.
Yeah, I'm sharing my presentation here.
Yeah, it's visible. Yeah, you can go. Yeah.
Okay. Can you guys see my PowerPoint?
Yeah.
Oh, okay.
Please start.
Okay. Yep. Good afternoon, everyone. Thank you, SARC Energy Center, and thank you, Mr. Tularam. To start,为什么这个一直跳出？To start today's presentation, I would like to have a short self-introduction. I'm Meng Wang from China, and I've been working as a software manager for over 7 years in PKPM Glory. PKPM Glory is one of the biggest building design software company in China. One of our team member, Ms. Yuan Bo, is here with me today. She is also specialized in HVAC design and building simulation. So maybe she will help me during the Q&A session. I just started Mr. Piz's presentation, and he talked a lot of details about the technical issues during the software simulation. But for me, I'm not going to talk a lot of details about how we do, how we will do the simulation work in China. Instead, I'll talk about to give you guys a more general idea about how China's building energy consumption is and what we are doing to control it from the government level. And I'll also share a case project to show you guys what we are doing in the actual project. So there will be 3 parts. The first one is the current situation. In these slides, I will give you some general idea about how China's building sector was developed in the 21st century. This chart here shows the completed building construction area from 2001 to 2018. We can see two different periods here. The first one is covered with this light gray rectangle. It's what we call the rapid growth period. It's from 2001 to 2011. During this period, we can see that the completed building area is rapidly increased. Because by that time, China is experiencing a rapid urbanization. Many people who used to work in the countryside start to move to the central city. A lot of residential buildings, public buildings were built. So by the year of 2011, we had over 25 billion square meters construction area, which is 1.7 times more than this number in 2001. Then we entered the second period. During this period, the total construction area per year is relatively stable. Every year, the data doesn't change much, and since 2014, we even start to have a negative growth in the following years. And in this slide, the two charts are showing the energy consumption structure in the world and in China. We can see that the total proportion of building energy consumption in China is quite similar to the world. In China is 37%, and in the world is 36%. However, because we still have a lot of construction going on, the construction percentage is much higher comparing to the world, which is 14%, and the operation percentage is lower, accounting for 23%. These two charts are showing the actual energy consumption during construction and operation. From the left chart, we can see that although the construction energy consumption is still very high, but because the urbanization has been slowed down, the total consumption per year has been better controlled since 2015. So we think if we can avoid large demolition and construction, extend the building life cycle, we can better control the total amount of the construction energy consumption in the following years. On the other hand, because we are having a huge existing building area in China, our society now are more focused on how to reduce the building operation energy consumption. So in the following chapters, I will talk more about how we are dealing with the building operation energy consumption. So before digging into any details, I would like to introduce a very important concept in China, is the energy efficiency rate. The concept of EER in China is a little bit different from other countries. One thing that is very interesting is, although it was called the energy efficiency rate, it actually does not use to calculate the actual energy consumption. It is used to calculate the reduction rate of the building envelope load, which means the EER is only related to building structure and thermal insulation materials. The HVAC systems were not considered. The other difference is the reference building we use. ER is the ratio of design building's envelope load to the reference building's envelope load. And the reference building we choose is the typical building built up in the 1980s. Because buildings at that time usually didn't have any external insulation, China's EER is a mandatory requirement. There are hundreds of different standards and different codes in different climate zones. Initially, the requirement of EER is only 30%. And now in most of cities in China, the requirement is already 75%. And even in some cold area, like the northeastern of China, the requirement is already 80%. So the calculation of EER is a complex and a dynamic process. Therefore, the engineers would need professional tools to finish this type of work. The first ER calculation software in China was developed by the company I'm working for, the PKPM Glory. Now more than 60% of the design institutes in the market are using this software to analyze the building load. By using this product, the engineer can calculate the building envelope load and selecting the air conditioning unit. At the same time, it can be used to analyze the load contribution of different building components. For example, if the external wall accounts for the largest proportion, it means the thermal performance of the external wall has the greatest impact on the building load. Then the designer can focus on adjusting the thickness or the parameters of the wall's insulation materials. Another thing that worth to mention is the engine we used. The engine of China's ER computing software is either DO2 or DAST. DO2 was developed by Lawrence Berkeley Laboratory in the United States, and more than, for now I think it's 130 different software developers have been using it as their calculation engine. The other we used mostly is DAST, which is independently developed by Tsinghua University in China. This engine contains the meteorological data of typical years in China, so it is much more convenient to the users in China. And the second developed trend is the green building and the healthy building. China has published 2 national assessment standards for green buildings and healthy buildings. And now we're using numbers of stars to represent the green and healthy degree of the buildings. Like we have the 3-star is the highest level, meaning the building is the most green or the most healthy, and 1 star is the basic level. The evaluation system of these 2 standards are very different. Green building standards are more about the structure safety, the durability, the resource saving. And healthy building is more about the air, the water quality, and the environment, which are closely related to human feelings and health. And because most of the calculation work of either green buildings or healthy buildings are carried out during the design phase, so we need simulation software to predict the future performance of these buildings. Usually we need to consider not only the energy consumption here, but also the ventilation, the daylight, noise, air quality, comfort, not only the indoor environment, but also the community environment, so we can make the final comprehensive decision. In most of the analysis work in other countries, the engineers would have to learn and use multiple software. So the model needs to be repeatedly established during the process. However, this part of work in China now has been simplified. Most software companies in China would have all this analysis in one software. So one single model only need to be built up once. And the common information like the insulation materials, the room information, the decorations only need to be set up once, which is very convenient for the Chinese users. And in order to make all these analysis tools better to adapt to different design platforms, because the architects are using all kinds of design tools, we have developed the plugin programs. The analysis software can be, there should be 4 animation. The analysis software can be used not only on the traditional AutoCAD, but also on SketchUp, Revit, or other BIM design software. And there are 4 animations here to show you the complete process of energy saving calculation on Revit. There are totally 4 steps. The first one is the design model on Revit need to be simplified and prepared so it can be calculated. The second is we need to modify the model. We can quickly add some components like the sun shading board here. And then we need to set up the parameters like the insulation materials or some special thermal properties. And finally, we can analyze and issue a report. And the whole process usually won't take more than 10 minutes. The third developing trend is the ultra-low energy buildings. I think in some European countries, we usually call this kind of buildings the zero energy buildings. But in China, the concept is a little bit different because we think the zero energy building is really hard to achieve. So we call it ultra-low energy building or the nearly zero energy building. It is actually the new fashion in China, especially in some cold area. The architect, the engineer would prefer to choose high performance insulation materials, better airtight doors and windows, and use renewable energy to achieve a very low energy consumption. These three projects are some of the presentive projects in China. The first project is a residential building, and the second is an exhibition building, and the third one is the office building of the parent company of PKPM, and it's also open to the visitors. If anyone comes to China and interested in visiting it, can make an appointment for visiting. And the last trend is the monitoring system and the sub-metering technology. Now, most of China's big cities require the large public buildings and the government buildings to collect energy consumption by using monitoring system. And here you can see this is the energy consumption monitoring system applied in our Shanghai office. In this project, we collect, here is the some real-time energy consumption and the equipment status of the HVAC system. And we also collect the environment information such as the carbon dioxide, the temperature and humidity. And then we made operation instructions for lighting and air conditioning system. And now in China, because of the coronavirus, I think people are more concerned about the comfort and the air quality indoors. So the monitoring system actually start to be very popular in some of the projects. And we also use a BIM model here. And furthermore, because we have the model here and we have some real-time collect parameters, we can analyze the status of the water pipes, the walls. We can analyze the hydraulic balance of the air conditioning water system. In the last part of today's presentation is a project case. This project is located in Shenzhen. It is one of the landmarking buildings in the local area. The construction design was finished last year, and now it's still under construction. My team was involved during the design process. This project will be used as the local art museum and library. The local climate here you can see compared to other cities in China is hot in summer and warm in winter. The temperature difference between winter and summer is not that much. The annual average temperature is around 22.5 centigrade, and the relative humidity is 77%, which is very high. So the comfort of the human body is a very important factor to consider in the architectural design. And to start this project, our team has a fully communication and discussion with the owner and the design teams. we have established 3 objectives. The first one is, from the models below, we can see there is a large area of glass curtain walls here that were used in this project. And we know that in area with high temperature and humidity, the heat transfer of the transparent components would have a great impact on the overall building energy consumption. So our first goal is to provide reasonable parameter suggestions of the curtain wall. And the second and the third is, just like Mr. PC has introduced, I'm very agreed with him that we always want to achieve the least energy with comfort. For the past decades, we only pursue, I think in China, we only pursue the least energy. Sometimes we sacrifice the comfort, but now people are more concerned about the indoor environment and how people are feeling inside the building. So the second goal is to optimize the design of the HVAC system, and comparing to the local mandatory requirements. There's a code in Shenzhen. We want to achieve a 16% less energy consumption. And the last but not least, we hope to improve the indoor environment comfort. So the first step here is to choose the suitable glass for the curtain wall. We wanted the glass to have a good insulation performance. Meanwhile, we don't want it to cost too much. So we decided to use 2 factors. One is the K value. K value is quite similar to the U value, and is the heat transfer coefficient. The other is the shading coefficient, represents the ability of glass to resist sunlight. So usually the smaller the shading coefficient is, the better the thermal performance of the curtain wall. So for each factor, we prepared 3 numbers and combined the 6 number into 9 scenarios. And then we have different simulation results. The results were showed below in the following tables and in this chart. In this chart, I don't know if you can see my mouse is moving here. It might be a little difficult to fully understand in this part because it has something to do with some specific parameters and China's special condition, but I'll try to make it simpler to understand. The gray dots here is the promotion rate of the curtain wall thermal performance. Here I need to explain. We think the performance of materials is related to the cost. So usually the higher the thermal performance is, the more expensive the materials will be. And the blue dots below the gray dots here is the reduction rate of the building load, which is the result we will achieve by taking those actions. So if we want to get the best result with a reasonable cost, we need to find the smallest gap between those 2 dots. So that is why we finally recommended scenario 3 instead other scenarios. And the second step is to analyze the thermal comfort. So similar to most commercial building projects, this project adopts the VAV system for the exhibition area and the fun coin unit for the office area. So we used CFD software to analyze the temperature, humidity, and air distribution inside the building. One thing we have noticed during the simulation is the atrium room. I forgot to show you the atrium room, so I'll have to go back to the slides before. Yeah, it's here. So we can see from the models here, there are 2 large area of skylights, and under the skylights there is the atrium. So back to this slide, we can see this is the result of the temperature distribution in the winter. So the heat supply is excessive actually. The temperature at the lower floor of the building is above 22 centigrade, and the temperature at the top of the building is higher, even higher, is over 30 centigrade. and the distribution of the temperature is quite uneven. So we made a suggestion to the HVAC design. First, we added some mechanical air exhaust devices here at the ceiling of the building. So it will accelerate the exhaust of the hot air at the top. And then we changed the location of the air returning device. So in the original design, the air returning device is at the ceiling. So the hot air returns from the top. And now we put it at the side walls and installed it at a lower position. So the hot air would returns from the side. And by using the new design, we re-simulated the environment comfort in winter. This is the result. The result shows the overall temperature is declined, not only the temperature at top of the building, but the average temperature of the lower floor can be controlled at around 18 centigrade. So by using similar simulation method, we analyzed the indoor temperature and humidity of all important areas and rooms in the buildings, and recalculated the comprehensive building load based on this calculation result. And then we suggested the HVAC system and the system parameters. In the last step is we used the energy consumption software to calculate the building energy efficiency. According to China's local requirements in this project, we only need to concern the energy consumption of the air conditioning system and the lighting system. So the elevators and other electricity equipment were not involved in the calculation. And finally, after calculation, the reduction rate of the energy consumption of this project has reached 17.5%. So basically, this is all for my presentation today. And because time is limited, I've only introduced, I guess, is the general process of China's practical project. We haven't gone into any details of the specific technical issues. And if you're interested in this area, we can talk about more. But one thing I have to mention is because we're either me or Ms. Yuanbo are not native speakers. So if you guys can slow down your questions, maybe we can better understand. Yeah.
Okay, thank you very much, Ms. Meng Wang, for your presentation, and the experience and presentation you share is very informative and meaningful, and you added some model project and their output to this presentation. Okay, now we move to the question. We have some questions from the participants. One question from Umar Mukhtar is, how does the software get the annual climate parameter? Is the whole world covered? He's asking. Okay, please. Hello.
Hello.
Yeah. Are you hearing me?
Can you repeat your question, because it's kind of hard to us to understand.
Yeah. Let me repeat. Yeah, I'll go slow. How does the software get the annual climate parameters? Is the whole world covered? Can you say this?
How does this software and
get the annual climate parameters? Climate parameters, maybe humidity, temperature.
So maybe I think we can organize all the questions and send me through the email. That would be better for us to communicate.
Okay, I will be more clear with the question. I will again ask the participant and I will tell you. Now, in another question is, in your simulation model, you provided some of the values, value. So what types of refrigerant gas is most common cooling in for cooling system? Can the types of gas be also specified in the software? In the software, have you specified the typical gas name?
I'm sorry, because it's really a little bit hard for us to fully understand. So maybe you guys can collect all the questions so I can respond it through the email or some other ways.
Miss Melanie, we
Yes.
are typing the question to you. Okay, we are typing the question to you.
Okay.
Okay. So before that, I have one question. Okay.
Yeah. Okay.
Okay. So in your presentation, yeah. Are you hearing me? In your presentation, you are talking about the local mandatory requirement. Yeah, local mandatory requirement.
Yeah, the local mandatory requirement.
Yeah. Can you say more elaborately on that? How that is
Yeah.
how that is being devised and implemented, that local mandatory requirement? Yeah.
I see one question here is how does the software get the annual climate parameters, right?
Yeah. You got it. Thank you.
Yeah, for this one, China's government has, we actually has different database according to different standards, because we have a lot of standards here, like I showed in this slide. Hold for a second. In this slide here, we have different standards, and in the standards, we actually has a database of the climate parameters. It was collected by the government, and the software only need to purchase the database, or sometimes the database are free in some place, and we can use this database to do the calculation. So this is for the first question.
Oh, okay. Thank you. So we are typing you another question.
The second question is.
Yeah. Yeah. You are getting the second question?
Yeah.
Check it, please. In your chat.
The second question is, what type of refrigerant gas is most common for cooling system, right? Is that one?
Yes, exactly.
Yeah, okay. Okay, Miss Yuanbo will answer this one because she's specialized in HVAC system.
Hello everyone. For the reference gas, now we usually use the liquid as a refrigerant rather than the gas because of the environmentally friendly rules. So we use water circulation in the building HVAC systems at the most.
In addition, the type of the gas is sure can be specified in the software, but only some certain type, not all the time. The types are also we have some common types, but the parameters of the different gas you can define by yourself.
Okay. Thank you very much, Ms. Mengling Wang. Thank you very much for your presentation.
Okay.
Thank you. We'll be in touch with you for coming time, and thank you very much for your time for being with us. Thank you.
Thank you. Sorry for my English speak. Haven't spoken English
It's
for
no
years.
problem. Yeah, it was very good. Yeah, thank you.
Thank you.
Dear participant, okay, dear participant, we have our third speaker is Mr. Asad Mehmood, is Manager Technical National Energy Efficiency and Conservation Authority or Energy Conservation Fund. And Mr. Asad Mehmood is a mechanical engineer by profession and is associated with the field of renewable energy and energy efficiency since last 15 years. He has played a vital role in the development and approval process of the National Energy Efficiency Act. Currently, he is working as a manager technical for National Energy Efficiency and Conservation Authority and company secretary of the Energy Conservation Fund. He is also a member of think tank of Pakistan Engineering Council on Energy and is going to talk about the addressing building performance simulation challenges. So over to Mr. Asad.
Hello, everyone. I hope my voice is clear to all of you.
Yeah, it's quite clear.
And screen is also visible.
Yeah, visible. Okay, you can go.
Okay, thank you. So going towards the last leg of the session for a shorter duration, I think that our previous two speakers have taken you to various dimensions of this specific specific aspects of the building energy simulation, and various case studies were discussed. So every region or every part of the world or continent, they have different approaches to address the issues, and everything starts with the policies and localized aspects which are the priority of the people living in that specific region. So coming to our part, the South Asian region, definitely the seasonal and temperature zones and climatic zones, there are many things which do overlap with many other countries or cities. But picking up the best practices from different models which are there, and their know-how and know-why basically are the key and crux to run a simulation of any particular building structure in an effective way by understanding the desired outcomes. Because there has been a continuous journey in advancement of all these building simulation softwares in many countries, and in our region particularly, many educational institutes, many research organizations are also teaching various building related softwares, building modeling, building architecture related softwares to the students. And then at the professional side, there comes the lacking where the real implementation aspects are considered. So so regarding my specific topic, everything starts with the real system, be it be any model, simulation model. There definitely is a starting point where the model is worked out, although the systems and softwares have been quite optimized by looking into various international applicable standards like ASHRAE, like green building guidelines, like edge building software. So there are different performance parameters which are there. The main thing is like the understanding the compatibility, the plugins, the graphical interfaces of all these simulation softwares. So right now we are also currently undergoing the process where the ECBC code, as our first speaker has just mentioned, that many of India and other countries, and in Pakistan we also had or have the ECBC codes, but the rules, regulations, and things like that are yet to be promulgated. But somehow, keeping in view international compliance parameters, the buildings have been constructed and are complying with many of the international criteria. And then simulation models are also run, have also been analyzed in determining the real-time energy utilization or performance of the buildings vis-a-vis the simulation results. So one of the factor that comes into the mind is like the uh, the 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 actual performance of the buildings when it comes to, and the deviation in the results as expected. So some buildings, once they are modeled or simulated, and once they are constructed, they might give you better performance, as a few case studies exist in Pakistan as well, where their buildings have performed much better than that of the simulations which were analyzed. It could be because of the disruptive technologies, or as our first speaker was mentioning about the immediate, like drastic breakthrough in the LED technology, lighting technology, and so many other ramping up of different building modules and building control systems. So these are like in a typical simulation process, all these experimentation and all these simulation results and analyzed, and the theoretical and the actual models are compared, and then they are practiced through various platforms which are available in the market. Like specifically when we talk about the building simulation process. So I think, yeah, okay. So when we talk about the basic concept of sequential simulation, as we have seen that through the graphical interfaces of our previous speakers, everything starts with the set of variables or set of information, which if it is not available, you don't build upon the building blocks of any simulation model. So fetching the data or correct data, because softwares are just like garbage in and garbage out. So if you don't get the right accurate data, or you don't have the know-how of using those specific values to analyze your results, that might not give you a good model. But it definitely, the good thing about simulation tools is like they give you the flexibility to exercise every good and bad into it, and see and analyze the results which are not possible in the real time simulations which you expect and look at. So the weather and building data, then the HVAC system data, plant data, and the cost related aspects which are mostly the variables. By keeping in view the country, like the rates or energy rates, they vary, or in other countries, definitely such variations definitely have an impact on your like simulation results, if you have like analyzed the results or predicted for the life cycle analysis of the buildings. So these things like, so rather than static simulation models, one might have to go towards dynamic simulation models in terms of life cycle costing analysis or simulation tools, if you are going to look at into the building structure. So various software tools which our previous colleagues have been working upon, and you might be, and many of our participants have worked upon as well. They are there in the market, they are there in the institutes, but they are not there where they really meant to be, like the building development authorities, or we also are struggling to like bring on a standardized or customized version of these softwares. Some of the earlier attempts which we had was like the Pennsylvania and Northwest National Laboratory. They also like they have one building system performance module with the name of FEDS. So we try to analyze the ECBC or performance parameters, or integrate it try to integrate it with those things. And similarly, as our current revision is going on for the ECBC codes, and our provincial designated agencies have also worked out on those parameters. So we look forward to have like sort of user interface or Excel based modules where like people in our development authorities, because of their low level of intellect or understanding, there should be some like checklists which would be available, and then the enlistment system for those credible energy modeling firms or energy modelers or database would be developed, whose reports should be considered authentic under the rules or regulations which would be like coming up. and hopefully, like quite recently, we might be taking on board the subject specialist experts in this case as well. And similarly in many other like countries in India or in Sri Lanka, in few of our previous sessions or activities which were undertaken by SARC Energy Center, like building energy is taking a new trend, or it's coming a hot favorite topic because of the urbanization and things like that. So, but there is not a silver bullet solution again. Every case study has to be like analyzed in their own geometry, in their own climatic zones, and the technologies are available, readily available at their end or in their countries, in fact. So, like while analyzing different challenges in terms of simulation, and when we talk about simulation, it's not only the design thing which we need to look at, it's the building life cycle analysis, and then there are certain challenges which have to be addressed. In fact, while going through all these modulations or simulations, when we talk about buildings, if you can see, or this like famous or very informative chart, which was worked over by Lawrence Berkeley National Laboratories, and similarly, like with the advent of new upcoming disruptive technologies, there needs to be like definitely some additional changes which we want to see in the building energy simulation models, like in some European countries, the electric vehicle loads, they are going to be like coming up, or net metering regimes are there, selling the power to the grid and things like that. So and similarly, the battery storage systems, how they are going to be integrated into these simulation models, these are the things which we need to think quite like at this stage and interval, and then like how to develop those plugins into the softwares already which are available in the market or being extensively used by the building modelers. So when we talk about specific building design at the initial stages, like you can see the numbers and the challenge against it, 1 to 610, and the design stage addressing the building performance gap, modeling human building interactions. That is something which is not in the control of like it depends how many from which what are the policies which are there inside the building, are there any building operating procedures. So these are the things like which are not dependent or have to be integrated into the models, and their impact have to be analyzed. Similarly, the calibration of various appliances or their sensors and things which are into the building, that has to be also analyzed, and then modeling zero net energy buildings and grid responsive buildings. These are the things where we need to like have a sort of dynamic building energy simulations, rather than like leaving them. And as per the building classifications, we need to move in this way that which buildings are 24/7 operational. Residential buildings definitely are, but which are the major energy guzzlers? So building upon each block, the buildings translating or developing into a city. So what is what is the impact the buildings or the cluster of buildings are going to have on the city? And then the utility level things also have to be considered from the very initial stages, that what is going to be the integrated building performance simulation. So the prescriptive, once we go towards the prescriptive sort of compliance, the behaviors could be analyzed very easily. But once there are human building interactions related to those, or unplugged loads, phantom loads, so these are the things which could not be analyzed, and would remain a challenge in these building simulation softwares until unless they are like some corrective actions or some additional features are added, or checklists are added into those things. And similarly, once the new cities or new formulation of new building clusters comes into place, the urbanization or urban building modeling impacts, or the microclimatic zoning then comes into place. when there is a cluster of buildings within the same vicinity, then rather than relying on like the localized data, we need to then keeping in view the know-how and know-why or the best practices of dense urban cities. So we need to get some expert opinions, because it's not only the modelers or simulation modelers which can really give you the perfect results. It's the people or the occupants or the policy makers which also influence the simulation results. Just like one of the examples in Pakistan case, if you go towards building life cycle simulation analysis, the cost of energy would be like something, one of the variable factors which will definitely like keeps that keeps changing your results or your performance levels at the end of the day. Then you have to analyze, or retrofitting perspectives also have to be looked into from the very early stages, because there is a useful life of every product. So so depicting the upcoming technologies beforehand in the keeping that flexibility into the design stage, definitely that also have to work out. And with the upcoming new plugins, because there is an integrator of every like building energy simulator program, where we need to add plugins, and those plugins or compatibilities then are the real key to give you the desired results through simulation. So basic building envelope structure and things like that, there are many tools available, or in an integrated way, or HVAC system optimization tools, but integrating them and without compromising on the overall results of the overall building complex or building set of buildings, that is like that is the address or the issues, the problem which needs to be looked at. And similarly, like when we look into specific the technologies, with their price levels, your localized price levels, they also have to be embedded to give people like immediate access to the data which should be there. Like in Pakistan, their climatic zones, and the climatic data in the DOE models, or there used to be like 2 cities where the data was there. So the struggle, like we have been able to capture like various the climatic or weather data of various cities, but again, like it's full, because of the large area or because of the continuous changing weather patterns. One can go for localized micro climatic zoning, and this is the research area or another issue or problem which our researchers or academics have to look into, and to be very specific about the building like developing a localized version, or localized simulation of the conditioned or a non-conditioned building. So and it will all thrive if the regulations come in time, and forcefully implemented. So that is the biggest barrier for the modelers themselves, because if the market demand is not there, then the business so the business relying on the business on the energy modeling definitely becomes an issue. So the policymakers have to play their role as the number one problem to address, and the problems of the modelers as well. So I've given you different perspectives in this through this single slide, and try to cover within time of which was allocated for this specific session. So there were like there was a detailed presentation, but I tried to be very crisp, and because having a sort of hands-on experience on different softwares available in the market, eQuest or DOE or other models, like and being from the regulatory side, regulatory perspective, like taking an overall I've tried to put up an overall perspective from the user end side, and from the regulator side. So that's the bottom line. Thank you very much for your patience and listening.
Thank you, Mr. Asad, for your presentation. And in the short time also you provided and you shared the things. Uh, Yeah, I agree with you because those who have the software and the knowledge in place, but in order to localize those software and to customize, there are some challenges from the developer side as well as from the policy level. Uh, so I have a question for you. So can you share some light on most common modeling software used in Pakistan for ensuring energy efficiency in building? Yeah.
Well, as already like we have discussed, like there are various set of softwares which are being used, and like it all depends upon the level of expertise or people have. Like Autodesk is like take Revit, and then similarly Energy Plus is something which is being taught in the universities as well. And like and then few of the designers under for green building or lead building certifications are also like analyzing these softwares where they are analyzing various other aspects related to these building integrators and thing and HVAC system analysis. So normally DOE is the first name that comes into the market, DOE Energy Plus, and then the eQuest is something like which people are now not very well comfortable to use as per our perception. So they are tilting towards like focusing on Autodesk or the Energy Plus versions or design builder. So their integrated models are being worked out by various modeling or design firms which are working for green building certifications at the moment.
Okay, perfect. So you are saying the Autodesk and Energy Plus are mostly used. In the same sense, another question from Milab Shrestha from Nepal is asking, um, top two software would you recommend? Which top two software would you recommend? He's asking. Okay.
While like the trial and tested like the softwares which are like trial tested and many other countries are using already, like I already discussed like those softwares with you, but there are definitely certain limitations when you talk about your own countries. The not every data would be available, and then there are certain rights or licenses which you have to take. So and the channel and there are various platforms from where you can reach out to those software or modeling firms. Like in Pakistan, there are representatives for like Autodesk or other some other softwares like Bentley, and so that's how like you can reach out to them, get the market-based data if you don't have them. So for the research perspective, you can like always analyze or get directly in connections with the software developers or software firms as well. That would be quite handy.
Okay, thank you. So another question is from Umar. How does the government implement and ensure building codes? Does the law carry any penalties for those who don't follow the codes?
Well,
This is
before
yeah.
penalizing or before like there should be a market enabling environment, and similarly like there should be some incentivized programs because of which trade-offs there should be some trade-offs because of which the real estate developers or the building owners try to invest on efficiency aspects. And it's the role of the utility provider as well not to provide the utility connection until and unless they go towards building energy simulations. So now we are looking into, there are development authorities, and then at the end of the day the electricity connections are provided by the utility companies. So that is the area where we are aiming, where so in order to just go towards at least prescriptive compliance of the building code. So that is something like where the building inspectors and electrical inspectors also have to play their role apart from the building energy modelers.
Okay, thank you, Asad. So Thank you very much for your presentation. So we are coming to the end of webinar, and with this, I may like to conclude our webinar. Thank you everyone for managing time and attending the session in this difficult time of COVID-19 pandemic. Thank you presenters for your very informative and interesting presentation. All the presentation will be available on Shark Energy Center website www.sharkenergy.org very shortly. We would love to hear from you any suggestion and comments for further improvement, plus any suggested topics of your interest for future webinar. Thank you, Deputy Director Sweep sir, for guiding us, and thank you, Umar, Ammar, and Wahab for your technical support. With this, me signing out. Thank you again for joining us today, and looking forward to see you next time. Bye bye.